Okay, let's get started with lecture 11. So last time we continued the discussion of simple harmonic oscillators, and in particular we talked a bit about energy, right? So there was kinetic energy, 1/2 m, let's say, velocity squared, and the velocity is of course a function of time, sinusoidal function of time, and there was the potential energy, 1/2 k, the spring constant. So that's a small k, that's a capital K. Displacement squared, or how much the spring is stretched or compressed squared, basically the displacement from the equilibrium position. And we had the energy conservation condition that k plus u is constant, and that's equal to k max, and that's equal to u max. So the maximum of the potential energy occurs when the kinetic energy is 0. That's at the turning point when x is equal to a, or plus or minus a. And the maximum of kinetic energy occurs when the potential energy is 0, and that's at x equals 0. So when x is equal 0, velocity is maximum. And when x is equal to plus or minus a, at the turning points, the velocity is 0. One important thing we found from using energy conservation and, of course, the kinematics of simple harmonic motion, namely x of t being a cosine omega t plus the phase constant, and v of t being minus a omega sine omega t plus the phase constant. So from these and energy conservation, basically these constraints that the maximum kinetic energy is equal to the maximum potential energy, we found that omega squared was k over m, or omega is the square root of k over m. So the spring constant and the mass determine the frequency, the physical characteristics of the system uniquely determine the frequency at which it will oscillate. All right, so today I mainly want to talk about the dynamics of simple harmonic motion. So we relate these to Newton's second law. We talk about forces in the context of simple harmonic motion. And we'll talk a little bit about vertical springs, so a mass hanging in the presence of gravity from a spring instead of moving on a horizontal surface. So it's going to be very similar, but there are a few differences that's worth talking about. So, but before going there, in the last lecture we ended with a problem, right? There was a practice problem using energy conservation, and hopefully you've all worked it out. So let's go back to this problem and try to solve it together. All right, so what was the problem? Well, we have a 500-gram block on a spring. It's pulled a distance 20 centimeters and released, and the subsequent oscillations are measured to have a period of 0.8 seconds. So part A is asking at what position or positions is the block's speed equal to something, to 1 meter per second. Right, so if we apply the energy conservation, so let's collect what's known here. So we're doing example 15.4. So So A, the amplitude is 0.2 meters, right? That's what's given to us, because we pull it away from the equilibrium position by 20 centimeters and let it go. T, the period is 0.8 seconds. And the mass is half a kilogram, right? 0.5 kg. So now we're saying if V is equal, if the absolute value of V is equal to 1 meter per second, that's the speed, can be either going to the left or right, so V can be plus or minus 1. What is X, right? Where would the object have that speed? That's what part A is asking. And a quick way to solve this problem is, of course, using energy conservation. So if I write U plus K as a constant, so therefore 1/2 mv squared plus 1/2 kx squared is equal to the total energy, which is 1/2 ka squared, right? When x is equal to its maximum, the kinetic energy is 0. Okay, so we find from here that let's say we cancel out the 1/2s. So, and I keep x squared on one side. So let's say kx squared is ka squared minus mv squared. Okay, so we don't really know what k is, right? But we know the period. So if I know the period, I know omega. And remember, omega was square root of k over n. So if I know the period, I can figure out the ratio of k over n, right? Because omega is 2 pi over the period. So this implies that square root k over n is 2 pi over t. Now here you see, if I divide by k, for example, if I'm interested in x squared, I can find x squared is a squared minus m over k v squared. And m over k, if you square this and kind of switch numerator and denominator, we find that's t over 2 pi squared. Okay? So putting all of this together, x squared is going to be a squared minus t over 2 pi squared v squared. And then at the values of x where this happens, where the velocity is v squared, which is what the problem is asking, is going to be plus or minus square root of that. So if we want to plug in numbers, that's 0.2 squared minus 0.8 over 2 pi, which is 0.4 over pi squared. And yeah, and v squared was, v is 1, the v we're interested in, or v squared we're interested in is 1. So that's supposed to be the answer in meters. Let's see if we did it correctly. So Playing from here. Right, so that's basically the energy conservation. And yeah, so that seems about right. So we have 0.2 squared minus 1 over, let's say, 7.85 squared. And so we have this 0.2 squared, and yeah, and pi divided by 0.4 is like 31.4 divided by 4, which is, yeah, 7 point something. Sounds about right. Okay, so we found the positions where that speed appears. Part B is asking us to find the spring constant, and that's also easy, right? We're given what the mass is. So that was part A. Part A of the problem. Part B is asking us to find the spring constant. So again, we're given the period. We know that m over k is equal to t over 2 pi squared. So k becomes m times 2 pi over t squared, right? If I multiply both sides of this equation by 2 pi over t squared, m gets multiplied by 2 pi over t quantity squared, and it cancels this t over 2 pi quantity squared. And then I multiply both sides by k, so on this side I get k times 1, which is k, and on this side I get rid of the k in the denominator. So that's our answer. And we can just plug in numbers. So that's going to be, the mass was 0.5 kilograms. So that's 0.5 times 2 pi over 0.8 squared. The units of k, right? The force is k times the distance. So that should be Newton over meters. And another way to think about it is, of course, F is equal to NA, right? So it's kilogram meter over second squared, which cancels that meter. So it's kilogram over second squared. And that works, right? Because this 0.5 here is in kilograms, this 0.8 is in seconds, and the 2 pi is just a dimensionless number. Again, if you plug that into a calculator, you're going to get a number. All right. Okay. Yeah, the number is 31 newtons per meter. Okay, so as we discussed before, right, for this type of dynamics, we have the acceleration is minus omega squared x, right? So even with the phase constant in the more general case, we've seen this several times, but it's worth repeating it. So let's say dynamics of simple harmonic motion. So the kinematics was x of t is a cosine omega t plus a phase constant. Velocity was the derivative of this minus a omega cosine, sine, right? The derivative of cosine is minus sine. And the acceleration is the derivative of the velocity, so that gives me minus a omega squared. I get another factor of omega from the derivative of the argument of the sine, and the derivative of sine is a cosine, so that's omega t plus phi naught. But a times cosine omega t plus phi naught is just x, so that's minus omega squared x of t. Now if I have F equal ma, and if you have a force that's proportional to the distance and in the opposite direction, like what you get from a spring, right? So if I pull it, let's say that's the equilibrium position, the spring gets stretched for a positive x, and then the force it applies to this object of mass m is going to be to the left, so that's minus k times x. And so putting these together, we find that if you have a force that's proportional to the displacement, we get the acceleration is minus k over m, right, if you divide both sides of these equations by m times x. So that's another way of relating omega to k and m, right? It's Newton's second law. It's also consistent with simple harmonic motion if omega squared is k over m, which is what we saw before from energy conservation. And omega is the square root of k over m. All right, so here's a quick question about forces. So pause the video, take a few seconds, and try to find the correct answer. All right, so we have a mass that oscillates on a horizontal spring, and its velocity is vx, and the spring exerts a force fx. Okay. At the time indicated by the arrow, so this is a plot of position, right? Position x versus time. So as usual, position goes between minus a and a. The period is the distance between two peaks. Okay, so at this point where x is at minus a, what can we say about velocity and force? Okay, so what is the velocity? I think that's something we've seen before. There are multiple ways to think about it, right? So one is, first, the velocity is the derivative of position versus time. So the tangent to this curve is a horizontal line. So its slope is 0, the velocity must be 0. Another way is when the particle is reached all the way to minus a, well, that's the maximum it can go to, so it must turn back, so the velocity must change sign. And then when you change sign, you go to 0, you go through 0, so the velocity has to be 0. Another way is that's the maximum displacement, you have the maximum potential energy, so your kinetic energy is 0. So yeah, so the velocity must be 0, so A, B, and C are incorrect. We're left with D and E. And then we want to see what is the sign of the force, right? So again, you're all the way at minus a, negative position, right? And then the force is of course pulling you toward the equilibrium position. So it must be to the right. And also we can use the equation, right? F is minus k times x. K is a positive number, minus k is negative, and x is negative, so F must be positive. So D is the correct answer. Here's another one. So basically the same setup, but a different time. Okay, so pause the video and try to find the correct answer here as well. All right. So now we're at a different time. We're at the time when x is 0, so the particle is going through the equilibrium position. So now what can we say about the velocity, right? So it's at x equals 0 at this point in time. A little bit later, it's going to be at a negative x. So it has moved to the left, right? So the velocity is negative, right? You can think about the slope of this line, slope of tangent to this curve again at that point is negative. So that leaves us with C, even if we didn't know about forces, but of course C is in fact correct because x is 0 and F is minus k times x. So at the equilibrium position, there is no force, right? The spring is not stretched or compressed, and it's not applying any force. So the acceleration at that point is 0. All right. Okay, so now the next thing we want to do is to talk about a mass on a spring that's vertical. So it's oscillating in the vertical direction. So let's see. Okay, so first, you'd notice that if the mass is in equilibrium, right, if it's not moving, you're just hanging a mass from a spring. Well, that spring must be stretched with respect to its natural length. So let's say this is the natural unstretched spring. And here, that's the equilibrium position. So let's say it's stretched by some length L, right? And it's hanging in equilibrium. Okay, so what is L first? Well, we can think about a Freebody diagram for this mass, right? There's going to be the force of gravity downwards, so there's going to be mg, and the spring is pulling it up. And the magnitude of the force from the spring is KL. Okay. So KL must be equal to mg for the equilibrium position, or L is mg over k. So that's the first difference between a horizontal spring and a vertical spring, right? For a horizontal spring, the equilibrium position corresponds to the natural unstretched length of the spring. Here, the equilibrium position has shifted down with respect to the natural unstretched length by some length L, which is just mg over k, because if it's in equilibrium, if it's not moving, the weight of the particle or the mass that's hanging must be compensated for by the force from the spring. All right, so that's the first difference. Now let's consider, pulling the mass down a little bit away from its equilibrium position. So let's say here is our mass again. That's the unstretched length of the spring. This is the equilibrium position. So let's say now from here to here it's L. And then we maybe pull it down a little bit more. So let's say we have some length y here. And this is our mass. So now what is the net force on this mass? Right? So first, let's again draw a free body diagram. So there's going to be again mg downward, and the upward force on this mass is going to be k times L plus y. Okay, so, right, because the spring from its natural length is stretched by L plus y. But that's, we know mg is equal to KL, right? So it's going to cancel out. So this is basically the net force is going to Ky upward, right? The KL, right, K times L plus Y is KL plus Ky. And KL is mg, right? Is mg plus Ky. So, mg here. So mg cancels with this mg, mg upward cancels with this mg downward. So the net force is again very much similar to the horizontal spring. It's just K times how much you've moved the mass away from its equilibrium position. And it's in the opposite direction, right? So I pulled it down. So let's say in this case my y is negative if you consider a coordinate system like this. And then I got an upward force, which is, you can think of it. So if I think about like put in some coordinate system and assigning signs to these things, it's going to be minus Ky, right? Because if it's a positive thing upward, that's minus Ky. In this figure, we just kind of wrote the magnitudes of the forces and showed the direction by arrows. But in general, I can again write net F is minus Ky, where y is the displacement from the equilibrium position. So let's say that's the equilibrium position. Okay, this is the y-axis here. So if you compress it, if you push it up from the equilibrium position, you have a positive y and then you get a downward force. And if you stretch it down like this, like the example we studied, the y is negative, and then the force we get is upward. So this minus sign works. So now we're going to get the same equations, right? Because again, F net is equal to ma, and a, the acceleration here, is the second derivative of y with respect to time. So again, our equations are the same as before. So the acceleration becomes minus k over m times y, and this is the second derivative of y with respect to time. So therefore, again, we have the same angular frequency as before, and we can write the same general solution. So y of t is again some amplitude cosine omega t plus phi naught, etc., and similar equations for derivatives. So it's basically mathematically the same as horizontal springs, except the equilibrium position is somewhere else. It's not the natural unstretched length of the spring, it's the length that the spring would have if you just hang a mass from it and let it come to rest, right? So the important thing is this y, this distance, is measured from the equilibrium position. You oscillate symmetrically around the equilibrium position. Okay? Okay, let's also think a little bit about energy in this context. So If we just naively think about, well, this mapped to motion when we had a horizontal spring, if we just substitute the distance with this y, which is the distance from the new equilibrium position, well, it seems maybe we can write u to be equal to 1/2 k, the spring constant, times y squared, and the kinetic energy, as usual, to be 1/2 mv squared, where v is just the derivative of y with respect to time, right? Okay, so that's obvious, right? The kinetic energy is always 1/2 mass times v squared. However, this needs a little bit more thought, right? Because the energy that's stored in the spring is, of course, more than that. The spring is stretched, if y is negative, like if you pull it down from the equilibrium position like that, there's more energy stored in the spring because it's stretched by some length that's larger. Okay, so how can we make sense of that? Well, the potential energy is not only the energy in the spring, but there's also the gravitational energy of this mass, right? If this mass moves down, its potential energy goes down by mg times the distance it has moved down. So let's see if we can derive this. So I can write g, or u rather, the potential energy as 1/2 k plus y, k times L plus y squared, right? So let's say again, that's the natural length. This is equilibrium, so natural equilibrium. And let's say you move down by some other distance y. So here I'm treating y as a positive number. It's just some length that's added. Now if we set, let's say, the origin for our gravitational potential energy here at the equilibrium point, this mass has come down by a length y. So its potential energy, gravitational potential energy, has come down by mgy. So that's gravitational. And that is, let's say, elastic. The energy stored in the stretched spring. Okay, so what is this? Well, I can expand out L plus y squared. So I'm going to get 1/2 k L squared plus y squared plus 2Ly minus mgy. Let's now recall that mg was equal to kl, right? That was the first condition that determined the equilibrium position, right? The force of the spring at the equilibrium position should cancel out the weight. So this I can write as, so let's write it over here. It's 1/2 k L squared plus y squared plus 2Ly minus KL y so that's going to be 1/2 KL squared plus 1/2 KY squared plus 1/2 cancels with 2, we get plus KLY minus KLY. These two go away. So we're left with this, and then there's a constant. But a constant never matters, right? So adding just a constant to R, potential energy doesn't affect anything. It doesn't depend on your position, right? It's just some number that's fixed. It depends on, let's say, the mass, right? KL is mg, so it's like, yeah. So K and mass just determine that constant. And notice that we made some arbitrary choice, right? By choosing the origin of the gravitational potential energy to be at the equilibrium position, we made a choice, right? It's always the differences in potential that matter. The absolute value of potential energy doesn't matter. It's some choices made. So we could have picked a different origin. We could have said, well, another point has zero gravitational potential energy by choice, so that that constant disappears. So yeah, so then this naive guess that we made, 1/2 ky squared, is actually fine, and we don't have to worry about these subtleties of like where the energy is stored, etc. Okay, so I think now is a good time to try to go through an example right here. Okay, so let's read this. Let's read through this together. Yeah, I made a quick edit. I guess that 83 kg was not showing. All right, so so you have this student who's hanging from a bungee cord, and the spring constant is 270 newtons per meter, right? So that's the student, that's the cord. The student's hanging there, and yeah, the student is pulled down to a point where the cord is 5 meters longer than its unstretched length, right? So that's where it's unstretched. There's going to be some equilibrium position somewhere, but you're pulling the student even further down. Now, and then release. So the student will be just oscillating up and down. And the question is, where is the student and what is his velocity 20 seconds later? Okay, so that's a really good problem. It combines a lot of things we've learned in studying oscillations. So yeah, so get a piece of paper and try to spend as much time. Let's see if you can push all the way through with this problem. Okay, so welcome back. Let's see how we can make progress. Okay, so first let's figure out where the equilibrium position is. So what is the amplitude, right? The amplitude is how much distance initially you move away from the equilibrium position. Okay, so it's just mg over k, right? We said, so here what we called L is called delta L. And so, yeah, so if you take G to be, let's see, so I don't know if G is taken to be 10 or 9.8 or, but yeah, if it's 10, it's roughly 830 divided by 270. So 3 times 270 will be 810. So yeah, so 9.8 is probably used. And we find, yeah, 3 meters. So from here to here is 3 meters, and the initial position is 5 meters from here, from the unstretched length. So that gives us A equal to 2 meters. Okay? So that's some progress, right? So we found A. Now we need to figure out y of t. So let's go back to the notes. So let's say we found L to be 3 meters. So let's say that's the equilibrium position. And then you oscillate between minus A, and A we found is 2 meters. So initially you're here, right? Y of t equals 0 is minus A. Okay, so going back to our circle, we're here. So I can write y of t to be A cosine omega t plus pi, right? From here to here I have an angle pi. All right. And what is omega? We know omega squared is k over m, right? So omega is the square root of k over m. And we're given these numbers. So I think that was 270. This was 83 square root. So let's see what the answer is here. Yeah, square root of k over m, so it's 1.8 rad per second. And A we know is 2 meters, right? So y of t is 2 cosine 1.8 times time plus pi. And that's an answer that's in meters. So then we're interested in the position of the student at a particular time, which is 2 seconds, so we just plug it in. And then we find the position. Similarly, if we want to find the velocity, we just use a general equation, right? We use the derivative of the general y equation, so it's minus omega a times sine of the same phase. And we plug in those numbers. And we find the position and the velocity. Okay, so to solve this problem, we had to think through a few steps, right? First, we had to figure out what the amplitude was from determining the equilibrium position, because the information we were given had to do with how much away from the natural unstretched length you are. And that's not the amplitude. When you have a vertical spring, you have to find the initial maximum displacement from the equilibrium position. So we found the equilibrium position, we subtracted these two to find A, the amplitude. We knew K, the spring constant, and the mass, so that gave us omega. And then knowing that initially the student is pulled down from the equilibrium position, so the initial position is minus A, we also found the phase constant phi naught. We put all of that together. Now that you have these numbers, we know the form of position as a function of time and these numbers, so we can determine it at some given time. And then similarly, we know the velocity and acceleration, etc. Okay, so what do you think about this? So pause the video, make a decision, and we'll come back and discuss it. All right. So when the block is at its lowest point, its acceleration is... What is the acceleration? Well, again, it just maps to a horizontal thing, right? So the acceleration is, again, minus omega squared times the distance. So if it's at the lowest point, it's below the equilibrium position. So that's a negative y. So the acceleration is upward. It's in the opposite direction, and it should be positive. Physically, it also makes sense, right? When it's gone all the way down, of course, the spring is stretched more than its equilibrium length, so the net force will be upward. It's pulling it up, and it will have an acceleration that's upward at that point. All right. So the next topic is the simple pendulum. That's another canonical example of simple harmonic motion. Okay, so we'll talk about the pendulum next time, but so today let's work out another quick example here. So let's say a spring is, so problem, spring is hanging from the ceiling if we attach a mass the spring is stretched by length L. What is the period of small oscillations around equilibrium? So the information we're given is just, how much the spring gets stretched at the equilibrium position. We're not given the mass, for example, or the spring constant, right? That's the only information we're given. And we're asked to determine, the period of small oscillations. So if you let it come down to L and then you stretch it a bit more, for example, from that new equilibrium position and let it go, what is the period of oscillations around this? Okay, so it seems like maybe L is not enough, but let's see. We can assume the things we're not given and see if the final result depends on something we don't know, right? So first, what can we say, right? So when the equilibrium length, the length the spring gets stretched at the equilibrium position is L, it means KL, the force of the spring, is mg. So we don't know K and M, but we can keep pushing. So that's one equation. And the period is related to omega. So we know omega is the square root of K over M. And the period T is 2 pi over omega, so that's 2 pi square root of M over K. Okay, so we notice that the period doesn't depend on the amplitude. It only depends on the ratio of M over K. And then we see that if we divide this by K, right, that ratio appears. So M over K is L over G. Right? So then we're good. Like the things we don't know kind of naturally don't appear in our final answer. And just knowing G and L is enough to figure out the period, the time it takes for one full cycle. So that's going to be square root of L over G. Okay, so that was a quick example where sometimes, in problems, we feel, oh, we don't know this, we don't know that. Well, we can assume the things we don't know, and maybe certain things don't depend on them. All right, so I think that's a good place to stop. So yeah, next time we'll continue our discussion of oscillations and we'll focus on pendulum.